वालेकुम सलाम। तो कल हम ये एग्जांपल किए थे बेटा, एग्जांपल नंबर क्वेश्चन नंबर 5। ओके, तो वेट अ मोमेंट। ओके, लेट्स गेट स्टार्ट। तो क्वेश्चन नंबर 5 जो है ना बेटा, सो दिस क्वेश्चन इज आस्क्ड इन नेट June 2014. So we have done it partially. Okay, so up to this point we have done it. But then I have kept it from assignment. Have you done this or not? ये एग्जांपल किया आपने बेटा, where suppose calculate price value of A if E1 is equal to 1.25 times E2. Okay, तो ये एग्जांपल हो गई। Should I show it to you or not?
No sir.
A का वैल्यू क्या निकला फिर? What is value of A finally? अगर आपने की है तो what is the value of A? You are not doing home assignment at your home. तो ध्यान रखो बेटा, okay? So what's given is this, E1 is equal to 1.25 times E2. So let me write down here E1 first of all. So E1 क्या है बेटा? That's equal to this. So E1 के बदले में लिखूंगा बेटा this 4 multiplied by rho naught. Okay, so here it's 4 multiplied by rho naught or divided by 8 epsilon naught. So here it is R divided by 8 epsilon naught. Fine. So it's like this. So E1 here we have calculated E1 here. So divided by 8 epsilon naught. So here I am going to write 8 epsilon naught. Then multiplied by this 1 by 3 minus A by 8. So here I will write down 1 by 3 minus A by 8 minus A divided by 8. Okay, so that's in turn equal to 1.25 multiplied by electrostatic field E2. And what's the electrostatic field E2? तो वो भी हमने निकाला है बेटा, that's equal to rho naught R divided by epsilon naught. So here I will write down it's equal to rho naught R divided by epsilon naught. Then multiplied by what? Multiplied by 1 by 3 minus A by 4. So here I will write down multiplied by 1 by 3 minus A divided by 4. Okay, fine. अब ध्यान रखो बेटा, okay? So first of all, this rho naught or divided by epsilon naught, it will cancel with this. So this here 4 by 8, so it is obviously equal to 1 by 2. Simply it's equal to 1 by 2. तो यहाँ आएगा बेटा 1 by 3 minus A divided by 8 will be equal to, that will be in turn equal to 1.25 multiplied with this here 1 by 3 minus A divided by 4. Fine. Then what I can write is this. So here it is equal to 1 by 2. So here it is 1 by 6. Then minus this here A divided by A to 16. So A by 16. And this here 1.25 divided by 3. So I will write here 1.25 divided by 3. Then here it is minus 1.25 multiplied by A divided by 4. Okay. Now what we are interested in is this. We are interested in calculating the value of A. So bring it here. Okay. So यहाँ ध्यान रखना. Concentrate here. So let's calculate the. We are trying to calculate the value of A. तो यहाँ ध्यान रखो बेटा. So it will be like this. This will be here 1.25 multiplied by A divided by 4. Okay. Then minus this. This will be here A by 16. So here I am writing it. It is A by 16 here. Okay. That's into an equal to what? That's into an equal this 1.25 by 3. So here I will write down 1.25 divided by 3 minus this term. Minus here 1 by 6. Okay. So here I will write down minus 1 by 6. Clear? Okay. So अब ध्यान रखो बेटा. Okay. So this here 1.25 divided by 4. Then here it is A. So what I can write is this. This here A by 4. First of all, I'll take this A by 4 common. Okay. तो यहाँ क्या बचेगा बेटा? यहाँ बचेगा 1.25 minus this here 1 by 4. And 1 by 4 is obviously equal to 0.25. 1 by 4 is 0.25. ठीक है ना बेटा? Then here it is 1.25 divided by 3. So what that will be equal to enter? What that will be equal to? Or I can write like this. I will write out here 1 by 3. Then here it is what? 1.25 minus 1 by 2. 1 by 2 is in turn equal to 0.5. Okay. तो यहाँ मैं क्या लिखूंगा बेटा? So here it will be A divided by 4 will be, and here it is 1.25 minus 0.25. That's obviously equal to 1, isn't it? And here this is equal to 1 by 3. Then 1.25 minus 0.5 will be equal to 0.75. Okay, 0.75. ठीक है ना बेटा? Okay. Now 0.75 will be in turn equal to 3 by 4. So I can write it like this. 1 by 3 multiplied with this I will write as 3 by 4. So this 3 and 3 will cancel this here 1 by 4. So simply it means that A divided by 4 is equal to 1 divided by 4. So simply final equation is this, that A divided by 4 is in turn equal to 1 by 4, which implies finally that the value of A is simply equal to 1. So यही है इसका आंसर. Okay. So the value of A that's equal to 1. Fine. Is this clear to you or not? कहीं पे रिवाइज करना है बेटा?
No sir, it is okay.
Okay. Okay, great. So we are done with the spherical symmetric charge distribution. Fine. Spherically symmetric electrostatic field. Okay. So we have used the Gauss law to calculate the electrostatic field due to the spherically symmetric charge distribution. Number one is that point charge, number second hollow sphere, number third solid sphere, which are the standard, and number fourth is that non-uniform solid. And cylindrical shell as well. And then we have done all the previous questions. Okay, which are asked in the net examination or just examination or paper examination. Fine. Okay. Now let's switch to another type of example. Line charge. Okay, so in this very case, the electric field has cylindrical symmetry. What it has? Cylindrical symmetry. Fine. Okay, now you are supposed to calculate electric field due to the infinite line charge. Okay, so let's try to calculate the electric field due to the infinite line charge. Okay, then you can memorize the final result. Okay, that will be simply equal to k lambda by r. So let me first of all calculate. Okay, so for example, here we have this an infinite long charged wire. Okay, so this is an infinite long charged wire, iron, which is uniformly charged. Okay, positively charged, uniform, infinite long wire, fine, whose charge density is given, it's equal to lambda. Okay, what is this lambda? This lambda is simply charge per unit length. It is charge per unit length. Now I have to calculate electrostatic field at this point. Suppose there exists this point, which is point P. It's at a distance of r from here, and we are interested in calculating electrostatic field at what point? At point P. Okay, if you want to calculate electrostatic field at point P, cylindrical symmetry. When it is cylindrical symmetry, so the Gaussian surface will be a coaxial cylinder. Okay, like this. So this will be the Gaussian cylinder. Fine. So it's a coaxial cylinder. Okay, whose length I can take. Its length is equal to L. Wait a moment. Its length will be obviously equal to L, and its radius is equal to R. Then next, what I will do is this: I will use the Gauss's law to calculate the flux and hence the electrostatic field through this Gaussian cylinder. Okay. So you wait a moment. Okay, so this is a Gaussian cylinder here. This one, this is a Gaussian cylinder. This is a Gaussian cylinder. Okay. Now this infinite long charged wire like this. Okay, so it's infinite long charged wire. Okay. So its length, the length of this Gaussian cylinder that I will take that's equal to L. That's equal to L. Fine. Okay. Now I have to calculate what? I have to use the Gauss's law to calculate the flux. Okay. So how I will do it? Just concentrate here. Okay, so what I will do is I will try to calculate the flux. Okay, so here it is. I will try to calculate the flux here using the Gauss law. So Gauss law is like this: integration of E dot dA. Integration of E dot dA for the closed surface will be equal to what? That will be equal to Q enclosed by epsilon. I will use the integral form. Fine. Now this will be obviously equal to what? So there are three different surfaces. Number one is this end cap and this end cap as well. The flux through these two end caps will be obviously equal to 0. The flux through this lateral surface area will be non-zero. Fine. So here I can take this as the area element. So this is the area element, fine, and this is dA vector that's in this direction. Which is the area vector here. Okay, dA vector. Okay, sorry. Then in the same direction there's electrostatic field as well, so that the angle between them is 0 degree. Fine. So that the flux through the lateral surface area is positive and the flux through the end caps is equal to 0. Then what this equation will be? Simply it will be equal to E multiplied by integration of dA like this. Fine. So that will be equal to Q enclosed. Now what is the charge that's enclosed? The charge enclosed is from this point to this point. Its length is L. So obviously Q enclosed will be safely, we can write it lambda into L divided by epsilon naught. Then here I can write it like this: E multiplied by this here lateral surface area of cylinder. That lateral surface area will be equal to circumference multiplied by length 2 pi r L. That's in turn equal to lambda L divided by epsilon naught. Then finally we are here that the electrostatic field will be equal to L and L will cancel. Lambda divided by 2 pi epsilon naught multiplied by r. Fine. You can also write it like this as well. We can write it like this: 2 lambda divided by 4 pi epsilon naught multiplied by r. We can write it like this as well. Remember that? Then this 1 by 4 pi epsilon naught is an electrostatic constant, and that's equal to K. So I can write like this: that electrostatic field finally it's equal to lambda divided by 2 pi epsilon naught multiplied by r, or it's in turn equal to 2K lambda divided by r. Right? So this is the electrostatic field. Okay. ठीक. अब जो डेव जे ग्रिफिथ है ना बेटा, उस पर ये this example is done already there. Okay. And then there's the discussion following this. Okay. The discussion is on this, that the electrostatic field with the line charge is proportional to 1 divided by r. Okay, there's a discussion, a big discussion on this, that the electrostatic field with the line charge is proportional to 1 divided by r. Okay, and it is equal to K lambda by r, where K is in turn equal to 1 by 4 pi epsilon naught. So we'll have to memorize this, give this standard result. Okay. Now, if for example you want to plot, you are supposed to plot the graph E versus R graph. So you are supposed to plot what? E versus R graph. So okay. So here we have this is R, the radial distance, and this is the electrostatic field, and you are supposed to calculate E versus R graph. Okay. So the graph will be obviously what? Rectangular hyperbola. Okay. So because E is proportional to 1 divided by R. Okay. But in case, for example, if the question is like this, that plot the E versus R graph for a point charge and for the line charge on the same graph. इसी तरह से यहाँ ध्यान रखना बेटा. Okay. So next example is this. Next example. Okay. इसी के साथ बेटा. It's like this, that plot E versus R graph, electrostatic field versus radial distance graph. Plot E versus R graph for point charge and line charge. For point and line charge. Point and line charge. ठीक है ना बेटा? एक ही जगह ये we have to plot both the graphs on the same graph, exactly on the same graph. Fine. So it will be like this. अच्छी तरह से यहाँ ध्यान रखना बेटा. So here it is. This is here E versus R. Okay, and you know that for the point charge, the electrostatic field is proportional to 1 divided by R square, and for the line charge, electrostatic field is proportional to 1 divided by R. Okay, that means the graph for the point charge as the line charge will be what? It will be rectangular hyperbola, isn't it? It will be rectangular hyperbola, but the steepness of the graph for electrostatic field of point charge will be more because E is proportional to 1 divided by R square. So the graph will be like this. Okay, so there will be two different graphs. So one graph will be like this, and another graph will be like this. Another graph will be like this. Okay, so this graph is for the line charge and this graph is for the point charge. Okay? So this is for the line charge, this one, and this one is for the point charge. The reason is that the electrostatic field due to the point charge is proportional to 1 divided by R square, and electrostatic field due to the line charge is proportional to 1 divided by R. So both will be rectangular hyperbolic graphs, but the steepness of the point charge of the electrostatic field due to point charge will be more because it dies down more rapidly with the R. Okay, so this is so we are done with what? The electrostatic field due to the line charge. Okay, you don't require this derivation at all, but what you require is the end result. It's really important. Electrostatic field due to the line charge will be equal to K lambda by R. Fine. Okay, great. Let's do a couple of examples here. If, for example, there are combination of wires, okay, the question can be asked on that as well. So यहाँ आप ध्यान रखो बेटा. Okay, so it's like this. So let's do a couple of examples here. Concentrate here. Okay, so suppose the example is like this. Here we have an example like this. Suppose there are two line charges like this. So here it is this here lambda, okay, plus lambda. Fine. It is positively charged wire, and then here we have this also plus lambda. This is also positively charged wire. Fine. Now here we have a point. So this is the point of interest, and which at a distance of R from this line charge, and at a distance of R from this line charge as well. Fine. And the question is like this: calculate the electrostatic field at the point P. You're supposed to calculate what? Electrostatic field at point P. Okay, so let's calculate the electrostatic field at point P. So this is the point P. We are supposed to calculate electrostatic field at point P. Simply what I will do is this: I will use the superposition principle. Fine. I'll calculate what is the electrostatic field due to the one line charge, and then electrostatic field due to the another line charge, and take care of the directions as well. Okay, so electrostatic field because of this will be obviously directed radially outwards. So in this direction it is equal to E. Fine. Then the electrostatic field because of this will be in this direction, and its magnitude is same, so it can be represented by E as well. Fine. Okay, now these two are mutually perpendicular, then their resultant must be somewhere here. It must be along this direction, and their resultant will be equal to root 2 multiplied by E. Okay, so that means the net electrostatic field at the point P, here I am going to write it. Net electrostatic field at the point P will be simply equal to what? That's equal to root 2 multiplied by E. Okay, so it's equal to root 2 multiplied by E के बदले क्या लिखेंगे? 2K lambda divided by R. It's equal to 2K lambda by R. Perfect. ठीक है बेटा? Okay, now there's another question. Let's do one more example. यहाँ और एक example कर लेते हैं बेटा. One more example is like this. Suppose that here we have two this here 1 and another lambda, two linear charge densities. Fine. This is here plus lambda, and this also plus lambda. Fine. And then at some point. So suppose at this very point. Fine. There's a charged particle placed at this very point whose charge is equal to Q, and its mass is equal to M. And this charged particle is placed in a gravity-free space. So here I am going to write it. It's gravity-free space. It's a gravity-free space. Okay. Now you tell me. So it is equidistant from this point as well as this point. So it is equidistant from here as well as here. Equidistant from these two line charges. Okay. So now the question is here: what is the net force on this charged particle? What is the net force on the charged particle? That's obviously equal to 0. because electrostatic field because of this and this is equal and opposite. Hence the force on this charged particle will be equal and opposite because of this line charge and because of this line charge. So the net force will be equal to 0. Now the next question is that is this charged particle in stable equilibrium or unstable equilibrium? Okay, so obviously it's in stable equilibrium. Stable equilibrium implies that suppose that what you will do is this, you will displace the charged particle towards right. That's for example, suppose that it's displaced towards right. Then it is displaced towards right. Now there will be net force on the charged particle, okay? And that net force will be towards point of equilibrium. So that force will tend to bring the charged particle back to equilibrium position. Now when it will return back to equilibrium position, it will not stop at this point, but what it will do is that it will overshoot its main position, and then it will oscillate like this, okay, executing simple harmonic motion. Okay, so you are supposed to calculate what you will have to calculate the time period. So okay, so what is the question is? The question is like this. If particle is displaced by distance x, particle is displaced by x, is displaced by x, small infinite small displacement. Calculate, you are supposed to calculate time period or calculate time period. Wait a second, calculate time period of the particle. Calculate time period of particle. Okay, so obviously it will execute simple harmonic motion and you will have to calculate time period of particle. You are supposed to calculate time period of particle. Okay, so what I will do is this. I'll be slightly displacing here. Okay, so this the problem is like this. So this here plus lambda and this here another plus lambda. Fine, this is plus lambda and this is plus lambda. Now suppose that, so initially it was at this 3 position. Now it's not here, it is displaced somewhere here by displacement of x, this charged particle q. Fine. Now obviously this distance will be equal to r minus x, this distance, and this distance will be equal to r plus x. So this distance will be equal to r minus x, and this distance from here to here, it will be equal to r plus x. R plus x, and the net force will be in this direction. That will be direct towards the equilibrium position. Is दिशा में होगा net force. Let's calculate that net force first of all. So first of all, let me calculate that force. So यहाँ ध्यान रखो बेटा, okay? So let's calculate that force. Now the force on the charged particle will be equal to this. It will be equal to this. So first of all, there are two forces. One because of this lambda. So that force will be equal to. So that is obviously equal to force is equal to Q multiplied by E1, okay, minus Q multiplied by E2, isn't it? Q multiplied by E1 minus Q multiplied by E1, E2. For example, suppose that this is here linear charge density. This is wire number 1 and this here wire number 2, okay. So on this charged particle, which is whose charge is equal to Q and mass equal to M, there are two forces. One force is because of this lambda 1 and another force is because of the wire number 2. So obviously the force because of the wire number 1 will be greater compared to the force due to the wire number 2, isn't it? So that means the force, net force will be what? F1 minus F2. That's what I'm writing here. The net force will be equal to Q times E1 minus Q times E2. Because if you want to calculate force, the force is simply equal to charge multiplied by field. Fine. Now this F is equal to here. So what I will do is this. I'll take this Q common, E1 minus E2. अब यहाँ E1 लिखेंगे बेटा. E1 is the electrostatic field because of this lambda 1. And what's that? That's equal to 2 multiplied by K into lambda divided by distance. And what is the distance? What is the separation between this and this? That's equal to R minus X. So यहाँ क्या लिखेंगे बेटा? R minus X. Fine. Then here it is minus. Here it's minus 2K lambda divided by R plus X. R plus X. Fine. So what I can take common is this. The force F will be equal to 2K lambda into Q. Then multiplied by this here 1 divided by R minus X minus 1 divided by R plus X. Go for the cross multiplication. It will be something like this. R plus X minus R minus plus X. Then divided by this here A minus B into A plus B. That's equal to A square minus B square. So R square minus X square. Okay. Fine. Then R and R is obviously going to cancel. X and X will add. So it will be 2X. So in the numerator it will be something like this. Okay. Concentrate here. So here we are. What we have to calculate is that net force. So let's calculate this net force. So net force क्या आएगा बेटा? So the numerator there will be x plus x is 2x. R and R is going to cancel. So 2x, 2 into 2 is 4. So here I will write down this equal to 4 multiplied by K into lambda into Q multiplied by x. Then in the denominator what we have is this. I'll impose the condition that x is very, very small compared to R. When x is very, very small compared to R, in that very case, R square minus x square is approximately equal to R square. देखो बेटा क्यों? Why? What's the reason? Suppose that this condition is not imposed here. If the x is not very small compared to r, in that very case, what will happen is this force will be no longer a linear function of x. It will not be a linear function of x. In the numerator, there will be something a linear function of x, but the denominator, it will be this x square will exist there, so it is not purely a linear function of x. And when the force on the charged particle is not a linear function of x, then it is never possible that the charged particle will execute simple harmonic motion, and we won't be able to calculate the time period in that very situation. Fine. Okay, that's why this condition is imposed. Now x is very small compared to r, so it means that x square will be even smaller compared to r square. So safely I can neglect this x square compared to r square. Like it's what? X square is suppose 1 millimeter and r is few meters. So obviously 1 millimeter square is very small compared to 1 meter square. It's like that. Okay, so the denominator we're left with only r square. Now obviously this is a function of x. Okay, that's what we want. It's a linear function of x. Okay? Now we have calculated this force. Okay, so number one, this force satisfies both the criteria. Number one criteria is that it's a linear function of x, and number second is that this f is anti-parallel to the x. For example, like this. आप देख लो बेटा यहाँ example. Okay, concentrate here. So the problem is like this: the force is obvious. The x is towards right and the force is towards left. That means f and x are anti-parallel. So that means this force satisfies both generalized equal m omega square x is the generalized equation for simple harmonic motion. Classical mechanics में आपने पढ़ा होगा. Okay. If not, then later on when we'll start the classical mechanics, so ये equations हम वहाँ पे अच्छी तरह से पढ़ेंगे. Okay. So till then, what you will have to do is that you will have to memorize. You will have to believe me that the simple harmonic motion is simply like this: m omega square x, where omega is the angular frequency of the charged particle, m is the mass, and x is the displacement. Okay. Now what will happen is this: x and x will cancel. So we can calculate from here what's the value of omega. Omega square, let me write down omega square. So this will be here 4 multiplied by k lambda q divided by mr square. Fine. Then you can also write it like this as well. K के बदले क्या लिखेंगे बेटा? 1 by 4 pi epsilon naught. 4 will cancel, so it will be lambda q divided by pi epsilon naught multiplied by m into r square. Then finally we can calculate the value of omega. Omega will be equal to under root of lambda multiplied by q divided by pi into epsilon naught multiplied by m into r square. So this is the omega. And then if you want to calculate time period will be equal to 2 pi, and reciprocal of this 2 pi by omega, so it will be here equal to pi epsilon naught multiplied by mr square divided by lambda into q. Okay, so this example can be asked in the competitive exam. That's why I shown this example here. Okay, so I'm sure ये आपको अच्छी तरह से समझ में आई होगी. Okay, so this example is now crystal clear to you. I think that. Okay, so simply what is it? The problem is like this. This is a charged particle. Okay, so obviously the net force on the charged particle is equal to 0. It is in equilibrium. Now the charged particle is stable equilibrium with respect to the x-axis, and with respect to y-axis, it's a neutral equilibrium. What do you mean by neutral equilibrium? That implies this: suppose the charged particle is displaced along the y direction, the net force on the charged particle will be always equal to 0, which means that it will neither move towards the equilibrium position nor it will move away from the equilibrium position. So every point will be a point of equilibrium. That is, every point on the y-axis will be a point of equilibrium. So that means this charged particle is in neutral equilibrium with respect to y-axis, and it is in stable equilibrium with respect to x-axis. Okay, that's what I want to say. Fine. Now this is a charged particle here. Okay, now slightly this charged particle displaced towards right or towards left. It's purely your choice. When it is displaced, so obviously the net force on charged particle will no longer be equal to 0. Okay, and you are supposed to calculate what is the time period of the charged particle. Obviously it will jiggle here and there like this about this mean position, and you are supposed to calculate what time period of the charged particle. Fine. Okay, so what I will do is this: wire thumb I will try to calculate what the net force on charged particle, and what I will make sure that that force which is on the charged particle must become a linear function of the displacement. Once it becomes a linear function of displacement, then it satisfies both the conditions for being a Hooke's law force. That is, condition number 1 is that it must be a linear function of x. Condition number 2 is that it must be always anti-parallel of the displacement, or it must be always directed towards the mean position. Okay, so here we are. Then we have calculated the force that's like this. There are two forces. They are anti-parallel to each other, unequal in magnitude. So that's equal to QE1 minus QE2. Then we can play with this equation, and then finally we can impose this condition here as well. We have to impose this condition. Okay, so that means the charged particle will execute simple harmonic motion only if the displacement is very small, or the amplitude of the charged particle is very small. Only then it will execute simple harmonic motion. Then we have calculated the force, and then here equated it with this m omega square x. Then you can finally calculate what the time period of the simple of this charged particle. Okay, great, perfect. ठीक है बेटा? I will keep a Humason for you. Okay, I will keep a Humason. Let me keep a Humason for you. Example is like this, that here we have, suppose this is here one charge density and one wire, and this here another wire. ठीक है ना बेटा? Now suppose that its charge density is something like plus 3 lambda. What's it? Plus 3 lambda. Its charge density is something like plus 5 lambda. And the separation between them is equal to R. Separation between them is equal to R. What you have to do is this, you will have to locate the point of equilibrium. So here I will write down locate point of equilibrium. Locate point of zero magnetic field, rather. Locate point of zero magnetic field. Sorry, zero electric field. I'm obsessed with magnetism. So locate point of zero electrostatic field. Or the question can be like this, where should a particle be placed so that the net force will be equal to zero? So the obviously charge particle must be placed somewhere in between. You will have to calculate, suppose the charge particle is placed somewhere here, suppose somewhere here. This is the point P, and this distance is equal to R1, and this distance is equal to R2. You will have to calculate what is the value of R1 and what is the value of R2. In terms of R. Okay. So this will stay as a Humason for you. I am sure आप ये कर पाओगे. Okay. So this example is a Humason for you. Now let's switch to this. Electric field due to the hollow charged cylinder. Electric field due to the hollow charged cylinder. Okay. So it's like this. For example, here we have this an infinite long charged cylinder, like this it is. An infinite long charged cylinder. Now what do we mean by infinite long? Infinite long doesn't mean that the charged cylinder is a few kilometers in length. What it means is that if, for example, this is a point here, and at this point there's observer like aunt, and this distance is very, very small compared to the length, then it will seem to this aunt as if the length of this is infinite large. That's what infinite large simply means. Infinite large doesn't necessarily mean that it is few kilometers in length. Okay, so yahan dhyan rakho beta. Okay, so it's like this infinite long, this what charged cylinder, hollow charged cylinder, or conducting simply, so that the charge if given to it, that will reside only on the surface. Okay, now the charge is given to it, so the charge is residing only on the surface. Now the question is that calculate the electrostatic field inside as well as outside. So this here it is given to you. Fine, this is charged here, and the charge density is given, that's equal to plus lambda. Charge density is given plus lambda, while lambda is simply what? Charge per unit length. Fine, its radius is given to you, that's equal to R. Okay, so here let me write down here, its radius is equal to that's R. So you are supposed to calculate what the electrostatic field inside as well as outside. Obviously electrostatic field inside will be equal to 0, because the reason is that if you assume a Gaussian cylinder, okay, if you assume a Gaussian cylinder that lies inside, the charge enclosed by the Gaussian cylinder will be obviously equal to 0. So then electrostatic field inside must be equal to 0. So electrostatic field is equal to 0 when small r is less than capital R. Fine. Okay, so electrostatic field inside must be equal to 0. Now we'll have to calculate electrostatic field outside. Okay, so electrostatic field outside, for example, this is a point here which is at a distance of r from this axis. This at a distance of r from axis, we are supposed to calculate what the electrostatic field at this very point. What I will do is this, I will imagine a Gaussian cylinder like this. This is the Gaussian cylinder, such that the point of interest lies on the surface of this Gaussian cylinder. Okay, so this is the Gaussian cylinder. Fine. Now we can safely calculate what is the electrostatic field here. Okay, so electrostatic field lines will be something like this. So in this direction there's electric field intensity, and the area vector can be taken in the same direction, so that the angle between E and D is equal to 0 degree. Fine. Then I can safely use the Gauss law here. Okay, so this is our A part, we are done with the A part, and B part is that we have to calculate electrostatic field outside. So I will use the Gauss law. Integration of E dot dA will be equal to Q enclosed by epsilon naught. Q enclosed by epsilon naught, and obviously Q enclosed will be equal to lambda multiplied by L divided by epsilon naught, because lambda is the charge per unit length. So if you want to calculate charge here, its length is equal to L. Length of this Gaussian cylinder is equal to L. Okay, this is equal to L. Now obviously the flux through these end caps will be equal to 0, because electric field lines will be running parallel to that, or the angle will be equal to 90 degrees. So the flux through the end caps will be equal to 0. Flux will be only through the lateral surface area. This integration will be simply equal to E multiplied by integration of dA, that will be equal to 2 pi r L. 2 pi small r multiplied by L, which is the lateral surface area of the Gaussian cylinder. Fine. That's in turn equal to lambda L divided by epsilon naught. This L and L is going to cancel, so the electrostatic field will be finally equal to this lambda divided by 2 pi epsilon naught multiplied by R. Or you can also write it like this, it's equal to 2k lambda divided by R. And the electrostatic field is obviously same as the line charge. So what does it mean? It means that if there's a hollow cylinder, electrostatic field inside will be equal to 0. Okay, so let me write it here. then electrostatic field inside will be equal to 0 when small r is less than capital R, and electrostatic field outside is same as that of the line charge, which is called 2k lambda divided by r, which implies that the electrostatic field outside is such that as if the whole charge of the cylinder is concentrated on the axis of the cylinder. Okay, ठीक है ना बेटा? And next is that you can plot the graph safely. Okay, you want to plot the graph, so here we can plot the graph. So here I will write down plot E versus R graph. Plot E versus R graph. ठीक है ना बेटा? So you are supposed to calculate plot the E versus R graph. You can do that with ease. So this will be the E versus R graph. So first of all, inside the electrostatic field is what? That is 0. Inside the electrostatic field, so this is your electrostatic field versus radial distance R. Inside it will be equal to 0. So here suppose it is equal to capital R. So up to capital R it will be equal to 0. Okay, so यहाँ से यहाँ तक 0 है. Then outside it is proportional 1 divided by R. That means it will be a rectangular hyperbolic graph like this. So here electrostatic field is proportional to 1 divided by R. So this is the graph for the electrostatic field versus R distance. Okay. तो कोई क्वेश्चन है यहाँ तक कोई क्वेश्चन है बेटा?
No, sir.
Okay, the speed is a bit faster. The reason is that ये तो आपने already पढ़ा होगा. Okay, that's why. ठीक. But we'll be doing later on some questions on this which are asked in the GATE, NET and JEST. Okay, we'll be doing those questions. Okay. Next up देख लो बेटा. Next question क्या है हमारे पास? Electric field due to the uniformly charged cylindrical shell. Okay, so cylindrical shell. Prior to that, there must be solid charged cylinder. Okay, so let's do this first of all. Electric field due to solid charged cylinder. Okay, let's do this example first of all. It's like up there, beta. So here what we have is this is cylinder. Fine. It's a solid cylinder, which implies that the charge will reside on the surface and inside the meat of the cylinder as well. It's an insulator. Okay, insulating cylinder. So the charge will obviously exist in the meat. So charge will be existing somewhere here. And in this very case, we are supposed to calculate. Suppose it's given to you the charge density of this is equal to rho. Charge density is given that is equal to rho. And the radius of the cylinder that's equal to r. Can you do this example yourself? Can you do this example yourself? ये example आप कर सकते हो? Will you be able to do this example yourself or not? Yes or no?
Yes, sir.
कट कर तो क्यों ना कट करें? Will you be able to do this example at your home? Okay, ये खुद कर लो, ठीक है ना बेटा? So I will give a hint. First of all, let you calculate the electrostatic field inside. So take a Gaussian cylinder inside, then take a Gaussian cylinder outside, then try it yourself. ठीक है ना बेटा? You will have to calculate in terms of rho. Okay, ठीक. The volume element here in this cylindrical coordinates, volume element will be what? That will be equal to it will be equal to pi r square L. Is it? It is equal to volume element will be equal to surface area. Sorry, and this circular area which is equal to pi r square multiplied by d tau will be equal to pi r square multiplied by L. Okay, where L is the length of this. Fine. Okay, L is the length of the Gaussian cylinder. So I'm sure ये आप कर पाओगे. Okay, and then let's do this example then. Okay, electric field to the uniformly charged cylindrical shell. I'll be showing this example to you. This example you will be doing yourself. So this I will give as a home assignment. I'm sure you must be able to do it. Okay. So यहाँ आप ध्यान रखो बेटा. Okay. So here we are supposed to calculate electrostatic field due to the cylindrical uniformly charged cylindrical shell. What I will do is this. I will.
सर जो आपने सिलेंडर का बोला ना, सवाल पे नहीं डी टाउ लगा सकते. एस डी एस डी फाइव डी जेड.
Exactly. But once you apply the limits of integration there, this exact limits of integration for what? For the s, it will be from 0 to L or from minus L to plus L.
Yes,
minus L by 2 to plus L by 2. You can take the limits of integration for s. Then for this, for s, you will have to take it from 0 to R. Sorry, for s. And then for z, you can take it from minus L by 2 to plus L by 2.
yes,
And then for the pi, you will have to take the limits of integration from 0 to 2 pi. Okay.
2 pi, yes,
ठीक है ना? Okay. तो वो आपको पता है ना? These cylindrical coordinates या वो हमें या वो मैं पढ़ा हूँ this cylindrical coordinates. क्या पता है आपको?
सब पता है, इसलिए बोला. वैसे भी कर सकते हैं ना?
हाँ, वैसे भी कर सकते हैं. Actually, this d tau is called pi r square L is actually derived from there. This actually derived from there.
Yes, sir.
This actually derived from there. Okay.
ठीक है सर.
Okay, great. Okay. तो यहाँ आप ध्यान रखो बेटा. Okay, so this you can do yourself. तो ये हम करने जा रहे हैं बेटा. That's electric field due to the uniformly charged cylindrical shell. Electric field due to the uniformly charged cylindrical shell. ठीक है ना बेटा? So it's like this. First of all, what I will do is this. Let me make a diagram here. So it's like this. Here it is. Cylindrical shell implies that it has some non-zero thickness. Okay, it has some inner radius and then outer radius, and then you are supposed to calculate the electrostatic field in the three different regions. In the three different regions. Okay, so here we have its radius is inner radius is given that's equal to A. This radius is given this A, and this radius is given that's equal to B, and the charge resides somewhere between A and B. Fine. Okay, it resides somewhere between the A and B. Okay, it's like this. Okay, so the charge here that's equal to 0. When the charge inside will be equal to 0, so obviously you can calculate the electrostatic field here. अब ध्यान रखो बेटा. So let me show it fast a bit fast. ठीक है ना बेटा? तो यहाँ आप ध्यान रखो बेटा. So charge density is given that's equal to rho. That's equal to rho. Okay, so let's calculate the electrostatic field inside. So A part is there, small r less than A, so obviously the electrostatic field will be equal to 0. We do not calculate that the electrostatic field will be simply equal to 0. ठीक है ना बेटा? B part is that let's calculate the electrostatic field somewhere between A and B. So here I will write down that the R is less than B, but it is greater than A. Electrostatic field will be non-zero. Right? So let me use the Gauss law. Integration of E dot dA will be equal to Q enclosed divided by epsilon naught. Q enclosed by epsilon naught, and this Q enclosed will be in turn replaced by integration of rho d or d top, one and the same thing. Fine. This integral will finally become equal to E multiplied by this is dA. D is this integration of dA, that is the lateral surface area of the Gaussian cylinder, which will be equal to 2 pi small r multiplied by L. Fine. And what is this L? This L is the length of the Gaussian cylinder. The Gaussian cylinder is something like this. This is that Gaussian cylinder, whose length is equal to L. Okay. And here what you can do is this. You can replace this dA by that this area element in the cylindrical coordinates. Fine. Or directly you can write down this E multiplied by 2 pi RL. Okay. So the competitive exams, what we'll be doing is this. We'll be directly writing down this. The area element here will be equal to 2 pi R multiplied by L. Simply it's what? It is circumference, which is equal to 2 pi R. So its radius is equal to R. Radius of this is equal to R. And the length of this Gaussian cylinder from here to here, that's equal to L. This length is equal to L. And the charge that's enclosed, the electrostatic field will be only because of the shaded portion. Okay, so because of the shaded portion, there will be electrostatic field at some point, suppose at this point or at this point, one and the same thing. Okay, so let's work it out. So यहाँ क्या आएगा बेटा? This will be here equal to rho divided by epsilon naught, because rho is a constant. You can pull it out of the integral. Integration of this will be here what? It will be here d tau, that's equal to pi r square multiplied by L. Pi r square multiplied by L, which is d tau. ठीक है ना बेटा? Okay, pi r square, wait, it will be not pi r square L. Wait a second, d tau will not be equal to pi r square L. I am sorry for that. Okay, तो यहाँ आपको थोड़ा सा change करना पड़ेगा. Okay, d tau will be how much? D tau will be equal, this rho is a constant, pull it out. It will be equal to 2 pi r multiplied by L, which is the circumference, which is the surface area of the Gaussian cylinder, multiplied by dr. Okay, this will be the volume element. 2 pi r L into dr. This will be the volume element. ठीक है ना बेटा? Actually, the limits of integration for that pi will be from 0 to 2 pi. तो वहां से 2 pi आएगा. Limits of integration for that z, for that exactly
S.
Z will from minus L by 2 to plus L by 2. This 2 pi L is a constant and equal to this here rho divided by epsilon naught. तो यहाँ बोलो rho divided by epsilon naught. This 2 pi L will cancel with 2 pi L. So you have integration. Okay, so r dr, the limits of integration will vary from where to where? Limits of integration will vary from A to R, because electrostatic field at this point will be contributed by only the shaded portion. So the limits of integration will be going from A to R. So यहाँ मैं लिखूँगा lower limit is A, upper limit is R. So A to R, and here it's what? It is here r dr. Okay, so let me write down here r dr. Right? So then finally it will be like this. This here E multiplied by R. E multiplied by R will be equal to rho divided by epsilon naught. Then here it is simply what? R square by 2.